Welcome to this video. In this session, you will be learning speed control of a stepper motor. We know that stepper motor is used in most of the industrial applications as well as in the robotics. For instance, if you want to move the arms of the robots, the stepper motor plays a vital role. For every kinetic motions of the arms, legs, at every node, one stepper motor will be there. The main advantage of stepper motor is that we can vary the stepper motor with the step angle. The step angle is a minimum angle made by the rotor of the shaft of the motor. Now in this experiment, let us see in the circuit diagram. You can see this is the stepper motor windings. 4 windings are there. And for the 4 windings, we have 4 switches. Every leg has 1 winding and 1 switch. So if you want to energize a particular winding, you have to activate this particular switch. So there are 4 switches which are there in all the 4 legs, one after the other. So now here we have 4 switches and 4 windings. At any instant, one winding from the A and B and one winding from the C and D you have to turn on, so that we get a step angle of 1.8 degrees. The 1.8 degree step angle we get because if you take a one revolution of 360 degrees, it takes 200 steps to go for a one revolution. So 360 degree by 200 is nothing but 1.8 degrees. So 1.8 degrees step angle of this stepper motor. And how to control the speed of the stepper motor? By using a digital controller. The digital controller is going to give the generation of the switching pulses given to these MOSFETs. You can observe the P is connected to the first MOSFET number 1 or Q1, which is going to energize the first winding, and Q is connected to the second MOSFET named as a Q2, which is going to energize the second winding. Third connection R is given to the third leg, and the same way S is connected to the fourth leg. So we have the 4 legs. We can energize whichever the winding we wanted to make it up, and ensure that at any instant one winding from your first leg and second leg and one winding from the third and fourth leg will be on. Then only we get a step angle of 1.8 degrees. Now in the stepper motor we have 2 modes of operation. So one is called as your step mode, where by pressing this button we get a 1.8 degrees, and one more is a continuous mode. In case of continuous mode, the rotor shaft is going to rotate at particular speed. The speed can be adjusted by varying this speed control knob. It is marked as a 0, 1, 2, 3, 4 up to 10. So by keeping this speed knob at different points, we can vary the speed of the stepper motor in continuous mode. Now we can rotate the stepper motor either in the forward direction or in the reverse direction, is by selecting this switch called as a forward or the reverse switch. The same thing we are going to see in your module of the stepper motor. Now this is the module of the stepper motor using a digital controller which is shown here. And PQRS are the digital output which is connected to the switches Q1, Q2, Q3, Q4 respectively. Now at any instant, one winding from the first and second leg and another winding from the third and fourth leg has to be activated for energization, so that we get a step angle here. And you can observe here, this is the forward and the reverse connections. In the sense, this toggle switch is going to rotate the motor either in the forward or in the reverse direction. Similarly, we have the second switch is called as step mode or the continuous mode. In case of continuous mode, the motor is going to rotate in a one particular direction. We can go either in the forward or the reverse direction. In the step mode, we are going to press this button to get a step angle of 1.8 degree every time. And apart from that, we see that we require minimum 15 volt for the stepper motor to work. And also, you can see here the motor windings, 4 windings are there. Across every winding, one diode is connected. So the main reason of this diode connection is that for a freewheeling operation, when the switch is closed, QN switch is closed, the current is flowing through the winding, through the switch back to the supply. And when the switch is opened, whatever the energy available in the winding has to be freewheeled through this diode. So that the freewheeling operation happens here only, energy available in the winding will be dissipated in the resistance of the winding itself. So the coil has to be reset every time. For that, diode is used. So that when the switch is in on state, power is flowing through the winding, so that the inductor coil will be energized. When the switch is in off state, energy available in the inductor coil will be freewheeled through the diode, and the energy will be dissipated in the resistance of the diode itself. Since the digital controller is very easy to operate, Now we have very simple connections here. We are going to have only 8 wires here. 2 wires we are going to tap from the VRPS. You can see the VRPS. From the VRPS, red and black, that is a positive and negative terminal, we are going to connect to the plus and minus of this module, stepper module. Then another 6 wires. You can see this is the actual stepper motor, which is we can see the stepper motor is the shaft of the stepper motor. So for angle measurement, we have a one pointer is there to see exactly how much degree it's going to deliver. Then these are the 6 leads which is come out from the stepper motor: A1, A2, A3, B1, B2, B3. The 6 leads has to be connected to the module. You can see here A1 wire hash color wire is connected to the A1 point of the your module. Then A2 has come to the Q1 point. A3 has come to the your Q2 point. Then B1 has come to this particular point here in the module. B2 has come to the B2 same point, and B3 has come to the same point, which means that A1 and B1 are the same potential. You can observe here. A1 B1 are the same potential. A2 leg 1, A3 leg 2, B2 leg 3, and B3 leg 4. So for all the 4 legs we have the connections taken from the A2 A3, B2 B3, where A1 and B1 are the common points which is shown here. And now let us see the operation of the stepper motor. We go to the step mode and we are going to see how much angle it's going to generate. Now let me put it in the 0 degrees. Put it in the 0 degrees. I go to the reverse mode. So I'll come back to the 0 point here. 0 point here. And I come to 0 point here. Now angle may be 0 degrees here. I'm going to press 25 times. So 25 times when I press 25 into 1.8 degree, because 1.8 degree step angle of this particular stepper motor. 25 into 1.8 is 45 degrees. Let us see how much angle we are going to cover by pressing this step button 25 times. Now I have selected the step mode. In the continuous mode, the motor will be running at the continuous mode. In the this may be forward or reverse direction. This is a forward direction, reverse direction. But in the step mode, we are going to measure the step angle also. So let us stop it at one particular point. So just readjust it to get to the 0 degree. Let me take the 0 degree operation there. I am the 0 degree right now. Now I am going to press this button, step button 25 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. 25. You can observe that it's all nearly meeting the 45 degrees, somewhere at 43 or 44 degrees. So there will be slight error will be there because of the friction of this pointer, whatever is shown there. But we are getting approximately 45 degrees. Now let me come back to the reverse direction. For that you have to take the button from forward to reverse mode. Move from forward to reverse mode. Now we are going to press this step control button 25 times so that it has come back from 45 to 0 degrees. Now let me press this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So nearly some small 1 degree error will be there, but otherwise we have covered the another 45 degrees in the reverse direction. We come back to almost to 0 degrees. So this is the step mode control. Now the step mode control actually we got by understanding the binary data how we got from the your digital controller. Let us see the digital controller table here. If you observe the table here, we have the connections given to A, B, C, D. So A is the first leg, B is the second leg, C is the third leg, and green is the fourth leg. But actually this refers to the red, orange, blue, green is the color of the wires that is coming out from the your stepper motor. Now if you observe here 0, 1, 0, 1, if you give this particular sequence from red and orange, so first or second leg is activated, second leg winding is energized. Blue and green, again fourth leg is activated, so fourth leg winding is energized. At any instant you can observe either red or orange or blue or green will be activated. So you can expect either 0 1 or 1 0 in this particular set. In this particular set either 0 or 1 0 we can expect. Now if you see the complete sequence, it is 0 1 0 1 nothing but 5, 0 1 1 0 6, 1 0 1 0 10, 1 0 0 1 9. Now when you want to go for a forward direction, this sequence will be generated here from the bottom to top. So we can expect 9 10 6 5. 9 10 6 5 in the forward direction, again continuation 9 10 6 5 9 10 6 5 every time. When you want to go for reverse direction, it will be coming from 5 6 10 9 and circulating the same way. Let us see the switching pattern here from the digital controller. I put it in the forward direction. Forward direction, then now the number is 6. After 6 it is 5. After 5 it is 9. Then 10. Then 6. 5. Then 9. 10. This sequence we get as per the table. When you go for reverse direction, now right now we are in 6. After 6 it should be 10 as per the table. So 1 0 1 0. This is the MSB. This is the LSB. 1 0 1 0. Then 9. 1 0 0 1 is 9. 0 1 0 1 is 5. And then 0 1 1 0 is a 6. Same pattern we can see in the table also. So we can go either forward or reverse direction. That's depending upon the switching pattern generated by this digital controller. Now this is a mode 1 operation where we go for a step mode. Then we go for a continuous mode. In case of continuous mode, move this toggle switch from the step mode to continuous mode. You can see the motor is rotating continuously. It's rotating continuously. And we are generating the pulses very at higher frequency. You can see here all are glowing green color, which means that all are giving pulses one after the other. Since all of them giving the pulses at very high frequency, high speed, we feel that all of them are glowing, but actually the generation of 5 6 10 9 is continuously it's coming to the all the switches. Now we are going to measure the speed of this stepper motor. And we have the two options here. We can measure either from the wristwatch. So maybe for 10 seconds how much revolutions are taken into 6 times. So we get for 60 seconds how many revolutions. Or also we can apply the formula to calculate the actual RPM. Let us see that particular table. Now the speed part position can be kept in 0, 2, 4, 6, 8, 10. The clock frequency we are going to measure from the CRO. Then calculated RPM is given by the formula. Speed in RPM is equal to 60 into clock frequency by N. N is the 200 number of steps. 200 is the number of steps. N is the number of steps. It's 200 exactly. So 600 into clock frequency from the CRO by 200. When you do that, we get the calculated RPM that we are going to write it here. Measured RPM using the wristwatch, and we can we can measure the RPM manually measure and write it here. Let us take few examples. So first we go to the step mode operation. In step mode operation, you can see the table 2. We press 25 pulses. We give the 25 pulses and see what is the angle covered by the shaft of your motor. Also we go for reverse direction. Just now we have seen it has taken 45 degrees to go front and 45 degrees to go back. So 25 pulses into 1.8 degrees is nothing but 45 degrees. That you have seen already. Let us go for a continuous running of the stepper motor. Now I'll set the step. I'll set the continuous step speed control knob to 0. 0 is a point I have taken. Then I am going to measure the clock frequency from the clock output knob and the common point here. Common point here. You can see in the CRO. You can see in the CRO. Let me increase the intensity. You can see in the CRO that a small dot is there. Small dot is there, which is the off time of the clock frequency. You can see the one more dot here. This is off time. In between you have the on time. On time I can show you by reducing the voltage. You can see the on time. Dots are running. So which means that the dot is the off time. From dot to another dot we have a on time of your clock frequency. So let me increase. So let us measure for 0 setting of your speed control knob. Let us see what's the frequency here. Now if you observe, off time I have kept at the left hand side. This is this dot. Before that we have a on time. Measure both total on time and off time here. When you measure, you are getting 1, 2, 3, 3.5 units into your timing is it is 1 millisecond. 3.5 to 1 millisecond is 3.5 milliseconds. 3.5 millisecond inversion. So when you do the 3.5 millisecond inversion, we get the clock frequency. So let us note down that the frequency is 1 by time, 1 by 3.5 milliseconds. So let us calculate that. So 1 over 3.5 milli, we are getting 285.7. So the first one is 287.5 hertz, right? So my formula is speed is equal to 60 into f by n. 60 f is 287.5, n is 200 steps to cover one revolution. So 285.7 into 60 divided by speed is that's n is number of steps, 200 steps. We are getting 85.7 rpm. So speed is 85.7 rpm. This is a calculated rpm from the formula. Now we go for a measured rpm. In the measured rpm, so I am going to check how many revolutions the shaft takes for 10 seconds. So I'll just watch, see the 10-second time where it starts. Then simultaneously I can see the how many revolutions it's taking. Let me see the starting point. Somewhere at 50 seconds I'll start. I'll say start. 1, 2, 4, 5, 6, 7, 8, 9, 10. For 10 seconds, you have to identify how many revolutions it has taken now. So maybe, so for 10 seconds, it's taken 12 revolutions. So 12 revolutions. So 12 into 10. That is nothing but 120. 120 10 seconds into 12. So it's a 120 rpm, but I am getting 85.75 rpm. So that's why I have to check the speed of the machine very carefully. Let us see that. Once again, let me check the your speed. Let me start now. My colleague will be helping out to identify the how many revolutions. I'll say start. She will identifying the how many revolutions has taken. Let me start. Let me say start. Start. Stop. 14. So it has taken 14 revolutions for 10 seconds. For 60 seconds, 14 into 6. So 14 into 6, nothing but 84 rpm. 84 rpm. So this is 84 rpm, which is nearly equal to my calculated rpm. So what we have done is for 10 seconds, it is taken 14 rpm. So for 1 minute or 60 seconds, we have to multiply into 6 here. So 14 into 60 is nothing but 84 rpm. That's what we have written here. So likewise, we can go for a continuous mode of operation. So let us take one more example. Let me set the step speed part position to maybe 6 somewhere here. Let me do that. I go to the 6 point number 6 here. The speed is increased in fact, and the frequency will also increase here. So let me measure the time period here. Coming somewhere around 1 to 2.7. 2.7 into 1 milli. So 2.7 into 1. 2.7 to 1 milli is 2.7 milli. So 2.7 milli is the time period. Inversion of that is my frequency. So 370 rpm. This is 370 hertz. Now I want to convert it to rpm. So 60 into f by n into 60 by 200. I'll be getting 111.11 rpm. Now let us see the measured rpm for 10 seconds. So my colleague will be helping out identifying. I'll say start, then I'll say stop, so that she will tell what's rpm. Start. Stop. 15. So 15 into 6. 15 into 6 is around 90. So this RPM will be maybe somewhere at 15 or 15.5 like that. If you take 15.5 into 6, it's coming out 93. So what we are getting is 111 RPM. So it's nearly matching. So this is 93 RPM. doesn't matter. If you measure very precisely, it may reach somewhere at 105 or 106 rpm. There will be some error because we have a manual error will be come into the picture. Otherwise, your measured rpm and calculated rpm will be similar. Okay, thank you. Hence, we can conclude that the stepper motor can be used to go for a either step mode control, where for every pressing of the button we can get 1.8 degrees, and for 200 times when you press it you will be getting totally 360 degrees. That's why the step angle is 360 by 200 is nothing but 1.8 degrees for this particular machine. And in case of continuous running mode, we have measured both calculated rpm and measured rpm. There will be some hardly some 3 to 4% error will be there. Otherwise, we come to know how to measure the calculated rpm and measured rpm. So in the practical situations, the people will go for either step mode to move the arm of the robotics for that matter, and for continuous mode to move the particular pattern of the robotics for the movement of the robotics, we go for a continuous mode. Hence, we can conclude that both calculated RPM and measured RPM are approximately same, and then we can able to achieve the step mode operation also in this particular case of the speed control of the stepper motor. Thank you.